Alright, so in this video lesson, I am going to show some more trig integrals right here as additional learning in terms of getting over with those trig integrals. So the first form I want to mention in this lesson is the integral of a form a power of secant and in product with a power of a tangent. And these two power are not necessarily the same power. They could be equal, but basically we have a product of a power of a secant and a power of a tangent. And so here we have an indefinite integral to handle over here. Okay. All right, and so now to get further into this, allow me to start with the first case right here, where we have in our particular integral, of course, a power of secant in product with a power of tangent as an indefinite integral. But I want to mention that now we're looking at the case where secant right here is even. Okay? So when secant is even. All right, so let's get into it. So specifically when secant is even, think about any even number is in the form of a 2 times k. Okay, so an even number is a multiple of some other integer over here. So in that way I can re-express this secant, the power of secant, so secant of x to the m power here, I can re-express that as the integral of secant to some power 2 to the k of x and multiply with tangent of x to the power n. And that's the starting. So that's just a re-expression knowing that our secant's power here is even. So in that way right here, the technique specifically good for this case right here. Again, this case is when the power on the secant is even. And so in that way right here, I can always separate out. So the power 2k right here, I am going to separate out as a secant of the power 2k minus 2 times the tangent to the power n of x, but times the secant square of x, and integrating that integral in respect to x. And so what I just did, as what I was saying earlier, I was separating out a power 2 right out from that beginning even power. So right from that beginning out power, I separate out a power 2, so a square of a secant x, I separate it out. So leaving behind, had a little typo over here, so leaving behind a secant 2k to the power, secant to the power of 2k minus 2 of x. Okay, and so that's the starting the step right there. And then consequently, after doing this, the integral will become, now notice that as a quick scratch work right here, 2k minus 2 can be factored as 2 times k minus 1. Okay, and so in that way right there, into our secant to the power 2k minus 2, I can think of that as a secant square of x, but raised to the power k minus 1. Because simply, again, as I mentioned earlier, 2k minus 2 means factoring out, after factoring out the common factor 2, it's 2 times in parentheses k minus 1. And so in the rule of powers, we're looking at secant square, and then overall raised to the power k minus 1. So that's just the rule for the algebraic rule for powers. And then, of course, we multiply with the tangent to the power n of x. And then we multiply with the secant squared of x dx. So that's just a generalized method of how we handle the case where the secant to the m to the power m, where m is even. But then how do we go further from here? Okay, and so now we can take advantage of that. As a reminder, we have that famous identity from trigonometry, that secant square of x equals tangent square of x plus 1, or you can write it the other way around, 1 plus tangent square of x. Like that. So I will do that substitutions right in the secant square like this. So secant square now can be substituted by tangent square of x plus 1. And so in that way, consequently, in the next step, the integral becomes 1 plus tangent squared of x. That's substituted for the secant squared of x. And in quantity raised to the power k minus 1. And we have an additional tangent to the n of x from previous step. And we have the extra secant square of x dx. All right, and so the unlocking key is right from here. Now, at this point, all right, and so upon arriving at 1 plus tangent squared of x to the power k minus 1 times tangent to the power n of x times secant square of x, I can now substitute tangent of x for u. So I can substitute u for tangent of x. And so in that way, consequently, du dx will be a secant square of x, which after rearranging the differentials du and dx, here I will get du equals secant square of x dx. And so that will substitute for this. And so the integral in the next step will become 1 plus, so tangent is now substituted by a u, so 1 plus u squared to the power k minus 1 times u to the n, and the secant square dx right here can be substituted by u. So we have completely turned our general the integral into an integral completely in terms of u, where it's simply a polynomial at this point. You have of course, you have to spend some time foiling out. That's the next point right here. You will FOIL out this binomial to the whatever k minus 1 power. After foiling that out, we will distribute this power u to the power n to each term. Okay, and then we're gonna start taking the integral term by term. Okay, and then that's how we arrive at the final answer like that. So this is a general instruction of how we can handle that trig integral, where it's a power of m, power of secant, and in product with the power of a tangent, but specifically the case where the power m, the power of the secant is even. All right, and so now let's get into an example where you can see how this works right here in real time. All right, so now we're looking at an example where we want to evaluate the integral of a secant to the 4th of x times tangent cube of x dx. So as introduced in the general guideline right there, this is a trig integral where we have a power of the secant in product with a power of a tangent. And specifically speaking, the power on the secant is even. And so now to proceed as guided from the general lecture right here, then I can rewrite this as a secant square of x times tangent cube of x, and separate out a secant squared of x here. Okay, so secant to the 4th is an even power, so I separate out a secant square of x from the secant to the 4th. And then the remaining power is a secant square for this problem right here. And so in the next step, it will become, so as mentioned earlier, secant square of x is equal to 1 plus tangent square of x. So I'm going to substitute this 1 plus tangent square of x into the secant square right here. So what I will have is a, in parentheses, 1 plus tangent squared of x, and multiply with tangent cube of x times secant square of x dx. And so now in my next step, I am going to substitute u for tangent of x. And so in that case right here, in this way right here, du dx will equal secant square of x. which will in turn become du equals secant square of x dx after rearranging the differentials dx and du. So now the integral will further become 1 plus u squared as I substitute tangent for u, as I substitute u for tangent. So 1 plus u squared times u cubed times secant square of x dx. So anywhere I see a tangent, I substitute the tangent by u. So that's what I get right here. Now secant square of x dx will now in turn be substituted by du. So the integral will further become 1 plus u squared to the power times u cubed times du. And so just as instructed in the general the guideline right there, then now I can just go ahead and this overall power of the 1 plus u squared is simply just power 1, so there's no need to FOIL. But in some other case when it's a high power, then we can just take some time FOILing that out. And now I'm going to distribute this u cubed for each term right here. And so that will give me u cubed plus u to the 5th power du. And the integral now is completely in terms of u, where we can just simply integrate term by term. And so first term will give me a 1/4 u to the 4th. Second term will give me plus a 1/6 u to the 6th. And don't forget plus c. And so now we're going to just simply substitute back the substitution that we chose for u right here. So our final integral, our final answer will become 1/4 tangent to the 4th of x plus 1/6 tangent to the 6th of x plus c. And this is how we found the integral. And so now we're in a different situation. Same integral, same kind of integral, where we have a power of the secant in product with a power of a tangent, of the tangent. But then now the situation here changed in a way that what about when the power m right here for the secant is odd? Okay. And so note one thing, this is just the arithmetic of numbers, it's just the nature of numbers. M is odd means m has to be in the form of a multiple of 2 but plus 1. You can also write it's a multiple of 2 minus 1, but here for this kind of problem, let's purposely write that as our power m for the secant can be written as a multiple of 2, that's why it's a 2k here, plus 1. The better form is writing like that, it's right here. So once again, m being odd, sorry for the equality right here, but really just m being odd means m can be expressed precisely or equal a multiple of 2 plus 1. Okay, and so in that way, let's bring that into our problem right here. So m equals 2k plus 1 right here means in our problem, it's a secant to the power of 2k plus 1 times with the tangent to the n of x. Okay, and so we have an integral like that. But now at this point, sadly, we have to split that into two separate cases. We have to really split that into two separate cases. So let's look at the case where, case 1. So once again, this is a sub-case where the power on the secant is odd. But now in this case right here, we got two sub-cases. So the first scenario here is when the power on the tangent is also odd. Okay, that further means n can also be written as a sum 2j plus 1 right there. Okay, sum 2j plus 1, some multiple of 2 plus 1. And that's this case specifically here. So our integral will really become, this integral from here will become the integral on the secant of the power 2k plus 1 of x times the tangent to the power 2j plus 1 of x dx. All right. And then with this current setting right here, we can now purposely isolate out a pair. So right now I'm going to isolate out and leave behind a secant to the power 2k of x times a tangent to the power 2j of x. So now note that both of these are all even now. But then I'm going to have a pair of secant of x times a tangent of x to be separated out like that as a product with the dx differential. All right. And so now upon that separation right here, I am going to get it on the other board. And so again, upon this separation right here, what we can do is we can make use of that famous identity again, that secant square of x will equal to and now from the known identity secant square of x equals tangent square of x plus 1, we can rearrange this identity as secant square of x minus 1 to equals tangent square of x. So now the plan is I am going to substitute the tangents to the power, the tangents to the even power right here with that, using that identity. And so here's how I'm making that substitution. The first thing, the secant to the 2k power, I am going to leave it the same. But the tangent to the power 2j right here, I am going to rewrite that as a tangent square of x raised to the j power. And then, of course, multiply with the secant of x times the tangent of x times dx. And so now I can put all of these substitution elements in there. So tangent square, as I said earlier, can be equal to secant square minus 1. So now I am going to substitute secant square minus 1 for tangent square in our current integral problem. So in the next step, the integral becomes the secant to the 2k power stays the same, but the tangent square now becomes a secant square of x minus 1, and of course to a j power, and then multiply with secant of x times a tangent of x dx. Okay, and so now at this point, I am going to substitute secant of x for a variable u right here. So by doing that, I am going to have, of course, du dx will be a secant of x times tangent of x. That's the famously known derivative for secant of x. And then I can rearrange, after rearranging the differentials du and dx here, I can see that du will equal to secant of x times tangent of x times dx differential. And so now this integral will simplify it down, or will get reduced to, so the secant to the power 2k will become u to the power 2k. Okay. The secant square minus 1 will become u square minus 1, but then the quantity raised to the j power. And then the secant x times tangent of x times dx right here can be substituted by a du. And so now we have simplified our integral and produced an integral entirely in terms of u, where after foiling out this u squared minus 1 in quantity to the j power and distributing out that u to the 2k to each term, you are going to end up with a polynomial, a simple polynomial. It could be lengthy, but it's a simple polynomial of all in terms of u completely. And then we can advance easily with this integral right here. All right, and so that is the first case of when the power m on the secant is odd. The first case here is when the n on the power n on the tangent is also odd, right? That was the plan of how we would handle that. And so now you can look at the following example to demonstrate the idea like that. All right. All right, and in this example, we are going to look at how we can find the integral for secant to the 5th times tangent to the 7th of x. And this integral here is a trig integral where we have a power of the secant in product with a power of the tangent. But furthermore, we recognize that the power on the secant is odd, as well as the power on the tangent is also odd. And so, according to the guideline, when both powers are odd like this, we can purposely separate out. So my secant to the 5th will become tangent, secant to the 4th of x. Tangent to the 7th will become tangent to the 6th of x. And I separated out a factor of secant of x and a factor of tangent of x. So this technique right here is shown in the general guidelines. And so now at this point right here, think of this tangent to the 6 right here. Tangent to the 6 is understood as tangent square of x raised to the 3rd power. And further, and so I'm going to rewrite that as secant to the 4th of x times tangent squared of x to the 3rd power, and times all of those extra secant of x and tangent of x dx. And then from trigonometry, we know that tangent square of x plus 1 must equal secant square of x. And so subtracting 1 from both sides, we're looking at tangent square of x will equal secant square of x minus 1. And so now the plan here is I am going to take this and substitute the secant square of x minus 1 for tangent square in the parentheses. So in the next step, the integral will become secant to the 4th of x times in parentheses secant squared of x minus 1 all cubed times secant of x times tangent of x dx. Okay, and so now at this point right here, on a side note, I am going to take a u substitution where I'm letting u to equal secant of x. So everything here is instructed from the general guidelines like that. So once letting u equal secant of x, then the derivative of u in terms of x du dx will equal secant of x times tangent of x, which will in turn give du equals secant of x times tangent of x dx after rearranging the differentials. And so the integral now will become an integral of u to the 4th as I substituted secant with u. And in parentheses, u squared minus 1, and open, close parentheses, to the 3rd power after I substituted secant by u. The secant of x, tangent of x times dx can now be substituted by du. So we have a du here. And so now this integral now is completely in terms of u. We can take some time foiling out this cubic of the u squared minus 1 right here. So in the next step, I'm just going to take some time foiling out this cubic. The FOIL product will give me u to the 6th minus 3 u to the 4th plus 3u squared minus 1 with a du. And anyone can quickly verify me of how I FOILed out this. So we can think of that cubic here as 3 identical factors, u squared minus 1 times u squared minus 1 times u squared minus 1. And so in the next step, the integral becomes u to the 10th minus 3u to the 8th plus 3u to the 6th minus u to the 4th. And I got that because I simply distributed the u to the 4th for each term in the parentheses here. All right, and so now we're just going to take the integral term by term. So first term will give me 1 over 11 u to the 11th. Next term minus 3/9 times u to the 9th, and we can later on simplify that. Plus, and now 3/7 times u to the 7th minus 1/5 times u to the 5th plus c. And so in the next step, I'll have 1 over 11 secant to the 11th of x, because we substituted u by secant, or we substituted secant by u. So now we're going to return the original variable. So 1 over 11 times secant to the 11th minus, now 3/9 from the previous step will now become a 1/3 secant to the 9th of x plus 3/7 irreducible times secant to the 7th of x minus 1/5 times secant to the 5th of x plus c. And that is how we have found the integral for secant to the 5th of x times tangent to the 7th of x, where both powers on the secant and on the tangent are odd. All right, and the next case, still we're under that situation, we're under that circumstance where the power on the power m on the secant of x is odd, meaning we can write m as a multiple of 2 plus 1. But then now let's look into the next case right here, the case number 2. What if the power n on the tangent right here is even, right, when we're in that situation? Okay. And so when n is even, now you have seen enough of my argument here, and your mathematical experience should be able to, with your mathematical experience, you should be able to understand this. But an even number is simply a multiple of a number, a multiple of 2. Okay, and so now n is an even number, so it's a multiple of 2. So in that case right here, we can rewrite this integral as secant to the power 2k plus 1 of x, okay, and then times tangent to the power 2j of x with a dx. All right, and so now with this situation here, with this problem here, the only way we can do right here, I am going to see the tangent to the power 2j as, so the secant to the power 2k plus 1 stays the same, but the tangent right here, I'm going to take advantage of that 2 times j power, so I'm going to write that as a tangent squared of x raised to the power j and with a dx. All right, and so now again we have from trigonometry that secant square of x minus 1 will be equal to tangent squared of x. Okay, and so I am going to take this information and substitute that for my tangent squared of x that was already in parentheses here. And so the tangent square will be substituted by secant square minus 1. So the integral will now become secant to the power 2k plus 1 of x times, in parentheses, a secant square of x minus 1 to the power j dx. Okay, and so now when we get to this point right here, we think about it, we can FOIL out this binomial in terms of secant square, and then we're going to have a lengthy polynomial after distributing all the secant to the power 2k plus 1 into each term right here. We're going to have a lengthy polynomial in terms of secant. Okay, a lengthy polynomial in terms of secants. You can write in decreasingly. But then after this point right here, you can use the reduction formula, the power reduction formula on all the secant terms, because you will end up with, after FOILing out, you will end up with simply just a whole bunch of secants, powers of secant, a whole bunch of terms with powers of secant and power of secants. And so you can use a reduction formula for secants to handle that particular problem right here, term by term. And so right from there, the only general instruction here, when you have secant times the secant square, so secant to the power of 2k plus 1, in times with, in parentheses, secant square minus 1 to the j, dj right here. So the only advice I have, we can use the power reduction formula for each secant to the power some power q of x dx, okay, in the overall integral. All right, and so for this generalized the instruction right here, then I have no prediction of how far it will get. So wait until we get into an actual example, and this advice will become a lot more clear. All right. All right, and so now in this example, we are looking at finding the integral for secant cube of x times tangent squared of x. But what's general in this example is that the power on the secant is odd, but the power on the tangent is even. And so from the general guideline that's given previously, we must use that trig identity. Tangent squared of x plus 1 equals secant squared of x. And so we can rearrange tangent square of x to equal secant square of x minus 1 after subtracting 1 from both sides. And so I am now going to substitute the tangent squared of x by secant squared of x minus 1. So in the next step, the integral becomes secant cube of x times, and now secant square of x minus 1. And so now I will have this secant cube of x distributed into each one of my terms in the parentheses here to make that secant to the fifth of x minus secant cube of x. All right, and so now from the general guidelines, the video lecture that was given previously, what we do now is to integrate this term by term. So I'm going to separate this out into one separate integral for secant to the fifth of x And I'm going to subtract secant to the third of x. And so at this point right here, once we're looking at simply just different integrals of single powers on the secant, single power on the secant. We got the power 5 here on the secant, power 3 here on the secant. We can use the power reduction formula on each of these right here. But so now with my experience that I've been teaching, then I will start out with only using the power reduction on that highest power first. All right, so right now we have the power reduction formula for secant here, and where we can apply this power reduction formula for secant, provided that the power n for secant has to be greater than or equal to 2. Okay, so in a way how the power reduction formula works right here. I'm going to use the power reduction first on this higher power right here. And so, according to the power reduction formula, the power 5 of the secant right here will give me, according to the formula, 1 over 4 times secant to the third power of x times tangent of x without an integral. And plus, now I have 3 over 4 times the integral of a secant cube of x dx. So this is the reduction formula. This is the result after applying the reduction formula on the secant to the fifth, on the integral of secant to the fifth of x. But now don't forget, we still have another integral to go. So minus the integral of secant cube of x dx. And so now at this point I have produced one finished term with two unfinished integrals, but they are now both in terms of the cube right here. So I can combine like terms, making it, now the finished term is here, 1/4 secant cube of x tangent of x. Combining these two as like terms right here, I'm looking at minus 1/4 and the integral of secant cube of x dx. And so now I can once again use the power reduction formula for this secant cubed, taking n right here as 3. And so here's how the next step comes out. 1/4 secant cube of x tangent x. That's the finished term. Minus, I recommend using parentheses. So minus 1/4, and then I'm going to use parentheses for this power reduction formula results to come out and be placed inside of the parentheses here. So in the formula, according to the formula, we have now 1 over 2 secant of x times tangent of x plus 1 over 2 integral of secant to the first power of x dx. And so we still have a little remaining integral, but the power on the secant keep getting reduced and keep getting reduced. And so now before moving over to the next step, I am going to distribute that negative 1/4 right here. So the first term, 1/4 secant cube of x times tangent of x, came from the previous steps, already finished. Now minus 1/4 times with that first term here, giving me minus 1/8 secant of x tangent of x, and then further minus 1/8 times the integral of secant of x dx. But note that at this point, for this secant of x right here, we can no longer use the power reduction because the power is 1. So we can no longer use the power reduction on this particular integral of secant of x. But now we know from some sided understanding that the integral on secant, we've learned previously that the integral of secant equals to natural log of, in absolute value, secant of x plus tangent of x plus c. And so now we can use this result that was learned previously and substitute that for substitute that for our the integral of secant of x, as this is the answer to that. So now my final answer will come out being 1/4 secant cube of x tangent of x minus 1/8 secant of x tangent of x minus 1/8 natural log of, in absolute value, secant of x plus tangent of x, and don't forget plus c. And that is how we have found our integral for secant cube of x times tangent squared of x, where the case here is that the power on the secant is odd and the power on the tangent is even.